A couple of announcements. One is the DigiKey parts from the April 9th order are in as of yesterday. And so pick them up. There'll be a new order on Monday, 8 a.m. as usual. I have to tell you that DigiKey parts get here much faster than all electronics. So all electronics, DigiKey almost always ships same day, except when I mess up. All electronics ships when they feel like it. Also want to remind you that it's 2 weeks and 1 weekend till the projects are due. And not one lab period so far this week has been half full, except for Wednesday night, which was almost full. So I know you have lots of other stuff to do, but we're now halfway, slightly over halfway through final project. The last thing is that I asked Atmel to send us some 1284 MCUs rather than 644s. I haven't seen them yet, but if they come in time, they have 4 times the RAM. They're the same speed, but have 4 times the RAM, 2 USARTs, 4 timers, 2 of which are 16-bit. And that's probably what we'll be using next year. Any questions about final project? What if Atmel never responds to your sample request? It's been known to happen. Last time, 2 years ago, the local salesman said that the corporate headquarters had sent him all of the requests, and he'd scrambled to find 50 CPUs because everybody requested them, and he managed to get them here the day the projects were due. So what we did was just say that anybody that had requested one got to, even if they, I mean, I essentially got compensated by the, I took the 50 that were given to me on, that were given to students, and we let everybody go free. So let's see what happens.
1284 have the same number of pins.
1284 has the same pin out and will work in the same development board. It's a 40-pin PDIP. It's just the internals are different, and some of the pin functions are a little different because you have to map more timers onto different pins. Maximum frequency is 20 megahertz. I haven't tried overclocking these. Anybody tried overclocking? Yes? You overclock lab 3, how high? 20 is not overclocked. They're spec to 20. They'll run 20. They're guaranteed to run 20. Question is, will they run 25? When I was trying overclocking the old 8515 parts, the first thing that failed was timer 1. But I don't know what to fail first. So I'd like to talk about the safety, some of the safety issues and some of the various things that have gone wrong, and it's relevant for an embedded control course because there are lots of systems we depend upon now that are more or less automatic, controlled by microcontrollers. And so let's talk a little bit about this Therac 25 disaster. I think there's no other way of saying it, but that it was a disaster. Who'd like to tell me what a Therac 25 is? Therac 25 is a linear accelerator, about 25 megavolts. Mega electron volts, right? So that's but since that means you're dropping an electron through a 25 megavolt field. That's what that means. Now it's probably not literally 25 megavolts. It's probably some sort of alternating gradient thing. But it's being accelerated 25 megavolts. So tell me, what is the rest mass in electron volts of an electron? Yes? That's grams. That's not electron volts. It's 511 kilo electron volts. And so that's about half a megavolt, half a mega electron volt. So 25 megavolt electrons are highly relativistic because everything is compared to their rest mass, right? So these are highly relativistic electrons. Why would you use electrons rather than X-rays for medical treatment? Yes? They won't penetrate as deeply. Actually, exactly the opposite is true. There's less surface damage. Exactly. Which means they penetrate deeper. In fact, as you know, X-ray absorption is always independent events, and they're always an X-ray absorption. If you look at depth versus dose, you always have an exponential decay with depth. Electrons are absorbed after multiple interactions. X-rays are absorbed after one interaction. Electrons are absorbed after multiple interactions. They bounce around like ping pong balls. So what you see is the higher the energy, actually the more absorbed deeper, and the higher the dose is at depth. So by tuning the energy, you can tune how deep you're putting the radiation damage. Or in this case, since they're using this to treat cancer, it's the radiation therapy. Why does radiation kill cancer? Well, put it differently, why does radiation kill cancer faster than it kills healthy cells? This is a biology question. Yeah. Right. The reason cancer is dangerous is that the cells reproduce quickly and without control, right? And so, since X-rays damage DNA, and DNA is being built very quickly in cancerous cells, you might guess that you could do more damage to them with X-rays or with radiation, and you would be right. It's not terribly effective. It's because your body takes a lot of damage also. Now, so let's just set a scale here. The LD50 for gamma radiation, that's the lethal dose for 50% of the population, is about 45 rads. And I don't care about defining these units because we're going to be doing everything in ratios. That's whole body. Yes, that's very important. That's whole body radiation. If you take 45 rads distributed over your whole body, you have a 50% chance of dying. If you take 45 rads through your foot, well, okay, probably nothing will happen to you. Take 45 rads, yes?
How is that determined? Obviously, they don't line up a bunch of people on the grass. Figure out how many die.
True. That would be a highly unethical thing to do, to line up people and blast them. Well, first of all, there's animal studies. Secondly, there are some combat events that have happened where people have been exposed to radiation. And there are also some terrifying experiments that were done accidentally at Los Alamos. Have you ever heard this? There's a an experiment that was done to figure out what the critical mass of uranium was, which was to set a half sphere of uranium on the table and then put another half sphere of uranium up here on a screw and drop it towards this half sphere until you had an increasing number of neutrons with time. And when that happened, you were just at the critical mass configuration. It's called tickling the dragon, for obvious reasons, right? This was the name of the experiment. And there were about 15 people in the room all watching this guy tickle the dragon. And he screwed up and dropped this onto here. And the neutron counters went off and the gamma counters went off, and he grabbed these things and pulled them apart. All right? And then he turned around and said, "Stop, nobody move." And he got out the tape and he measured the distance to every person so they could get the inverse square law, right? He measured distance to every person, and then he checked into the hospital and died about 4 days later. And from that, they got a very accurate whole body radiation dose on about 15 people, and they watched how many died. Yeah, not funny. It is. I mean, it's sort of totally bizarre, but it was a terrible thing to have happen. But it was a useful experiment. Yes. Probably. Yeah. It's a rather dramatic event. Enough radiation, a few of the people could taste ionized saliva. A few of the people saw Cherenkov radiation from the flash of light going from the X-rays going through the water in their eye. Okay, so this sets the scale of what's important. 40, 50 rads is a large dose of radiation.
How do they classify it as like 50 guys? If you get a lower dose, maybe because all cancer funding.
These are prompt deaths.
Okay.
Prompt means 60 days. Okay, so this thing is a LINAC. So linear accelerator. Out the end of this thing comes a beam of electrons about 1 millimeter across. Very intense beam of electrons. And then one of two devices are put in front of this thing to make it a therapeutic beam. One is 3 magnets, 3 electromagnets, so these are supposed to be coils here. And the current is modified in these coils to wiggle the beam around. It's called a wiggler. It moves the beam around in some pattern so that you get a uniform distribution of energy over a choosable size up to a few centimeters, 2 or 3 centimeters. And the other thing that was put into the beam sometimes is a wedge of tungsten. Why tungsten? You want to make X-rays. You want a uniform beam of X-rays to come out. So this is an X-ray converter. Why tungsten? Physics question. Huh? High melting point. Right, you're pouring a kilowatt into this thing. It's going to get hot. You don't want it to melt. And there's another thing too also, that tungsten has a fairly high Z, and X-ray production is proportional to atomic weight, number of protons. So this thing could have a wiggler put into the beam or an X-ray, and there was a big turntable with 3 ports in it, one of which is the X-ray port, one of which is the electron port, and the third port is a mirror. And the mirror was used to align the subject with the other windows. There's a light source that's calibrated to bounce off the mirror and to shine onto the patient where you want the radiation to go. So it's used to position the patient correctly with respect to the machine. And then when you get it all lined up, this thing spins into the correct position for either X-ray therapy or electron therapy. It's a big thing. Takes us a few seconds to move. So that's kind of the physical layout. There's a computer that controls this. Tell me about, who wants to tell me about the computer? You know a lot about it, don't you? Did you work with PDP-11s? Oh, you're not old enough for that. Yeah.
The computer was initially a non-essential component to the system. It sort of did a supporting task. It made operation easier, but everything was built into the hardware. That was where how.
So the error control was in the hardware, and the control stuff was in the hardware. That was for the Therac 20, right?
Yeah, talking about the transition from 20 to 25, and that's part of where things went wrong, is when they used the computer for what it wasn't even really necessary, I guess. They could do it in hardware, but it was easier to do it in software.
And because Therac 20 did not report any casualties at all, they assumed that the software would be pretty solid for 25.
Right. In fact, there was a decision made by management about that software was more reliable than hardware. And why was that?
Well, if software works,
I mean, it's bit accurate, right? It doesn't wear out like a switch does, so it should be better. Should be better.
Confused reliability with healthy.
Yeah, yeah. The confused reliability, several kinds of reliability.
As a commentary on the state of the art, in 1985, I doubled my computer memory by taking a one-hole punch and making my floppy disk two-sided.
Right.
Okay, how could somebody possibly remove hardware interlocks for a software-driven system in 1985? I was dumbfounded by it. Because they have hardware interlocks on standard things in every system in today's world.
That's right, and you're quite right. It's absolutely dumbfounding. It's beyond comprehension that you would take out the mechanical interlocks on this rotating platform. In the Therac 20, there were, and in the 25, there are 3 micro switches that could tell you exactly what position this plate was in. And in the Therac 20, there was a hardware lockout so that if the ports weren't correct, you couldn't fire the machine. And they eliminated those in the Therac 25 so that if the micro switches were in the right position, it fired with no hardware interlock. And I think part of the reason you see hardware interlocks on everything now is because of Therac 25. Because the idea there was software is godlike. Software that isn't written could do anything.
You ever played Space Invaders? Like they have?
Yeah. So I'm not justifying this. So yes, there was a management decision made to eliminate the hardware interlocks for reliability. Oh! There was another reason why they wanted to automate all this, and that is because the users wanted it. They're Speak up. Uh-huh.
So for 2 businesses with the same exact person, she sort of like put it in autopilot mode and just needed to go with that. And so the selected software timers didn't register a lot of things.
Right. So there were a bunch of system errors based on ease of use, and the ease of use was driven by the requirements of the operators who hated. I mean, this is a big wheel. You had to spin these things into position and lock them by hand. And they didn't like that. And it's slow, and they're doing a lot of these. A lot. What's a lot in this context? I doubt if it was several a day. I looked up, by the way, the current demographics in the U.S. says that about 41% of you will have cancer sometime in your lifetime, and of those, about 1/4 will die of it. And of those, probably most will be in an X-ray machine of some kind. So this is directly relevant.
10% of us are going to die.
About that, yes. Between 10 and 15%. No. Yes. The cancer is a probably well, cancer is a catch-all term for about 110 different diseases or so, and they all are related to misregulation of growth. And there is probably some balance in your body between growth and let's put it this way, you have to make sure that the stuff in your body is regulated, and so you have an immune system to kill off invaders, bacteria, viruses, rogue cells. You get a cell that mutates, suddenly has a weird capability like infinite growth, but its surface is modified. It can be recognized by the immune system and killed. The better your immune system is, the more likely you are to have an autoimmune disease. In other words, you'll start recognizing things as not yourself that are part of yourself. The worse your immune system is, the more likely you are to have cancerous kind of misregulation. There's a balancing act. There's a regulation balancing act that's been optimized by evolution to make people that live long enough to have kids. Cancer is a disease of older people who are past reproduction age, for the most part. Yes, this is serious stuff, and it affects you. So, the users requested this. The technicians who ran this equipment said, "Please, don't make me pull this hard disk around. Motorize it. Make it a servo system." And part of the data entry problem was that you got, now let's set the scenario here for the computer. It's a PDP-11. I used PDP-11s. It was the first lab computer I got my hands on. It was a 1976, 78 kind of computer. It was about this big, about, same mass as me, more or less, and ran at 0.1 million instructions a second, so 100,000 instructions a second. The Mega 644 would stomp it flat, right? It was programmed mostly in assembly at the time for efficiency. The user interface, imagine, if you will, a terminal with one window that looks like putty. That's all you've got is putty. Right. No windows, no widgets, no resizing. This thing is about that big, that deep, has a keyboard hard attached to it. A keyboard in the front here. And the only thing you can do, because this is a VT100, you can look that up, VT100, is that there was cursor control, so you could move the cursor around, so you could make a form. You could say, you could have fields on the screen where you could fill in values. And then the cursor would move back up there and you could type in this value. And what the technicians found was it was really easy to make a mistake, and you had to clear the form and go back up and fill in all the fields again. They hated it, because everybody makes mistakes. And so they made it editable. So you could hit the cursor keys, go cursor, 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 cursor up to this field, type, hit enter, and the data was re-entered. And a fast operator could do that very quickly. Why exactly was this a problem?
Well, it was sort of returning to a default value of maximum mega electron volts, right? I mean, when they hit the cursor, it was sort of screwing up the set dose.
That's true, and the reason is that there were at least 6 processes, 6 independent processes, and also another 5 or 6 interrupt service routines. So there are about 11 threads of control running simultaneously on this wimpy little machine, this little 100,000 instruction per second machine. And so I don't know what the context switch time was, but I bet it was pretty slow. And the programmer didn't know anything about synchronization of routines or semaphores. And so you backspace up, backspace, type, hit enter. The process that controls the screen knows that the update has been done. The process that controls the position of the wheel doesn't know. The process that fires the LINAC doesn't know that there's been a change. And the worst thing that has happened, the worst outcomes that happened because the computer knew that the X-ray spreader was in the beam, when in fact it was the mirror that was in the beam path. And so not only was there no beam spreading, there were no wiggler magnets, but there was no attenuation. This is 100-to-1 attenuation. And so when you ask for X-ray mode, it jacks the beam intensity up a factor of 100. So this thing got to the point where the mirror was in line, fired the LINAC, and hit people with thousands of times higher dose than they expected or desired to have.
Was the fact that when the machine pauses, the user just presses it again and does it 5 times until
Oh yes, there's right. There's this whole thing about completely incomprehensible error messages. Geez, that sounds like Windows almost. But yeah, so error 35. Press resume. Okay. And the technicians got very used to doing this because it happened all the time. And most of the time, there was not a problem. Most of the time, it was a real machine screw up, and you press resume, and it would recover and do the right thing. Except every now and then, these various tasks would be out of phase. But there was a really bad one related to a counter. Did anybody pick that? Yes.
Yeah, because it has a variable which kind of, if it's 0, then it means everything's fine.
Ready to go. 0 means ready to go. Yeah.
Otherwise, it will increment itself, but it's only 1 byte, which means after 256 times, it will goes back to 0 again.
Right. And so there was a variable that was set by being incremented rather than set. So if the variable was 0 and the operator pressed the button, the fire button, then the 0 meant ready to go and it would fire the beam. If the value of the variable was not 0 and the technician pushed the button, the system would wait until it was correct, and then until the value was 0, wait until everything was set up, and then fire the beam. Unfortunately, it was checking once a second, I think. Once a second, or twice a second. So about every 250 seconds or so, the not ready variable, the not ready counter would overflow to ready. And if you happen to push the button When it happened to overflow, it fired the beam no matter what condition the machine was in. Oh dear.
They didn't release any information about the actual person who did all this programming. Yeah. How was that possible?
So the outcome of this was, I mean, we haven't gotten to some of the more terrifying details, but the outcome is that, if I remember right, about 7 people were either injured or died. And none of the cases went to trial, and so the programmer was never interviewed, or his state of mind was never made public.
How did it come from?
Different times. I think they did, yes. They did rename themselves. It was different.
Privatized.
Well,
I don't know if that has anything to do with the accident.
I don't understand how it works.
so
Almost criminal neglect.
you're right. And at the time, the FDA didn't regulate medical radiation devices very well because they were brand new. So the rules were still getting built. The mechanisms were still coming into place. They were all out of court settles. Yeah, they settled on all of them, yeah.
Yeah, instead of fixing it right away, they were just sort of covering it up, all the cases, and then sorting it out of court, and that's it, and say it's fine.
And one of the covering up, yes, this was amazing how much the company stonewalled the FDA. It couldn't happen. It's impossible.
Put electrical tape on the button.
Yes.
How is the air not reproducible? Obviously, well, it seemed obvious to me that if users were getting the air fills frequently from using it, and the company claimed they tested it for 100 hours, the air could have popped up.
Well, the problem is that people that design code unconsciously test things in a way that doesn't break the code. I mean, if you know it's going to break when you type fast, you type slow. But also, you said they tested for about 100 hours, and that's right. Yes, go ahead.
So I think from what I understood reading it is that they did see a lot of errors in the field, and what happened, they called the technician and said, hey, I'm seeing this error, and the technician would go, well, the error is caused by something I know what's in the code, so they ignore that error and go on. Now after they called them 20 times saying we found this error, they didn't call them the 21st time.
Just say go. And part of this is that the failure time, the mean time to failure of this machine was more than 100 hours. And so if you test for 100 hours, you'll never see it. There was one hero in this thing. There was one hero in this whole thing who was the medical physicist at one of the hospitals. So we want to talk about that? He did some rigorous testing, and he also recognized after the company said that it couldn't possibly be radiation exposure, he recognized the burn pattern on the person's skin as there's things called beam shapers they use, which are essentially lead wedges that you put on the person to restrict the radiation even more than the beam position. And the grid of these beam shapers formed a pattern on the skin, which the physicists recognized as being from the spread, or from the grid producer. And so he knew that it was radiation exposure and that the machine had failed.
And before, when that happened, it was like they sort of set the reason to those patterns as like the woman had a heating pad or something like that.
Heating pad, right.
Yeah.
There's an X-ray. X-ray, yes, they X-rayed the heating pad looking for the wire pattern in it. So, in the Texas case, in Ontario, one of the first cases, 1985, the dose was 15 kilorads. All right, so it was almost 1,000 times higher than the LD50. And in the Texas and in Texas, the dose was 20 kilorads. So these were truly large doses that people were getting over a fairly small area. In one case, I think it was in the 1985 Georgia case, the beam was focused at the top left of the woman's breast and hit the shoulder, and there was no record of what happened because the printer was out of paper on the machine. And they fired this thing, destroyed all of the tissue in this quadrant of her chest, fused her shoulder. It destroyed the joint. It destroyed the aortic arch. It killed her. And but there was enough energy that she had surface burns on her back.
Yeah.
Right.
One of the readings said that the dose of a couple thousand rad was enough to kill someone 50% of the time. Why would they even make a machine that is capable of 15,000 or 25,000 if that would almost certainly kill someone?
Well, the idea is that you have to have, if you expect an X-ray exposure and you're getting the electron exposure, to get a reasonable treatment time, you have to get the intensity up so that you can get enough X-rays out, because you have 100-to-1 attenuation through the tungsten block. So it's not unreasonable that you'd want to have a high dose rate so that you could compensate for the attenuation of the X-ray producer and still have a reasonably short treatment time. People have to lay still for these things, and it's hard to get somebody to lay still for 10 minutes. And you ever had to lay still for, in an MRI machine or anything like that? It's tough. Don't twitch. Don't swallow. Oh, okay. And so you want it to be fast for the comfort of the patient and for the throughput of the machine. So there's a trade-off. But clearly the safety interlocks have to be there, so you can't actually give somebody a dose. Oh yes, both the X-ray port and the electron port had Geiger tubes on them. They had ionization detectors for getting the dose. The mirror didn't, because no radiation would ever come out of there. And so they didn't actually know. It wasn't an instrument to be able to tell what the dose was.
Well, they were saturated too. You wouldn't be
Oh yeah, these were saturated during the E-beam was saturated.
enough dose.
Yeah.
Right.
The dose was too low.
Dose is too low. Hit it again. In one case, in Texas, the second person killed. The video and audio link to the outside world was broken. Normally you'd watch the patient with a video link, and it was broken that day, and they fired it, and the person reported hearing crackling of their skin, and then the technician looked up because somebody is pounding on the door saying, "Let me out of here!" So the person got themselves up, and in that case the detector was saturated, so they had no idea what the dose was.
I didn't understand why repeatedly people would say they felt a burning sensation, and no one addressed that as an issue earlier on.
I don't know if you've ever been to a doctor who doesn't believe you.
But after hearing it from like 10 different people.
Well, it wasn't the same doctor. It was
Yeah,
different
it's
people
also
that
the-
heard it, so it wasn't
Maybe
lots
something
Compared
you
to
learn in
the
grad
doctor.
school.
And I mean, there's all kinds of psychosomatic things. You've this thing. I mean, I've had this happen. You go to the dentist, they put the thing up to you, they hit the thing. I swear I feel a tingling in my jaw. I can't. It's a tiny dose of radiation. But So people hallucinate sensations. And so you hear somebody say, well, I felt a burning where this was. Yeah, sure. But I mean, this is always a problem, yes.
Oh, I was just thinking, so I read an article about that. It was that they were given a recommendation to create an interlocking system separate. And they decided not to do that. So then why would they ever do that after obviously there are patients who had issues with the design?
Well, that's a good question. Why didn't they put the hardware back in for hardware interlock? And you can only imagine what the arguments must have been like in the boardroom. This is going to cost money. We believe that this machine is correct. Somebody might have stuck their neck out and said we should go all software. You know, it's impossible to tell why this wasn't done or how they got away with stonewalling for 5 years.
Almost until the FDA was like, well, listen, you'll be pulling this out.
Right. I mean, they did this for 5 years. Yes.
Well, a question about the malpractice though, like if they had changed the interlocking, then wouldn't that have indirectly proven that they are admitting that they did something incorrect, so they would have to pay more?
Yes, that's probably true. And I mean, it certainly happened with what was it? It was safeties on a Winchester rifle, I believe. If they had upgraded the safety on the Winchester rifle, they would have therefore shown that the old one was defective, and they would have had a whole bunch of suits they had to pay on. The defect was that if the safety's on, you pull the trigger, hold the trigger down, push the safety off, and the thing fires. Who in their right mind would do that? Well, a kid sitting in the back seat.
I thought it was if you turn the safety on, pull the trigger, and then release the trigger and release the safety in that order, it would still fire sometimes.
Oh, maybe that's true. Maybe that's true. I thought it was you pull it, hold it, push it, and the idea would be that if the safety is on, you should have to let everything go back to neutral. But you might be right on that also.
Yeah, and I remember actually some hospital when they heard about complaint from patients that they feel like burned, they actually asked they actually called the company to ask whether there's possibility of overexposure, but like the people at the company assured that this
Right.
is not possible.
They assured it wasn't possible. They totally stonewalled.
Yeah.
Can't be our hardware. Must be your operator. Operator error. It's mind-boggling. It's totally mind-boggling. Yes.
So I'd like a takeaway from this accident, like I guess the accountability is very important, and also like this is art, as students who are kind of like new projects. Like a lot of people just have the impression that their part of the project works, and so when they're like debugging together, they might be like, oh, my part's fine, especially my partner's problem, and like point fingers and that sort of thing. So it might be like, I guess the takeaway is like,
You have to get responsibility for the whole project. Well, that's a good takeaway for this. That there's lots of ways for a system to go wrong, and if you see something bad in some way, even if it's not your part of the project, if you see something that's wrong, you have to deal with it in some way. Now that can be tough. You know, you get various social scenarios where the boss says, you have to behave as a team. I want to see close interaction and teams supporting each other. What happens then when your team member is an idiot? And are you then going to go to the boss and rat him out? Well, what should you do, right? The boss says, work as a close team, support your teammates, but you know the guy's a fool. So it can become significantly difficult to do that socially. But you're right. I mean, that's one takeaway on this. Any other takeaways? What do you think about designing medical hardware?
What I was thinking while reading this is that we go through all these processes of debugging and building and designing, but we never really have anything on testing. We're not about testing.
You know,
Finish something for the deadline, we throw it there, we demo it, and it works this time, but when does it fail?
There's no coursework on project testing.
well, that's an interesting thing I've been trying to figure out how to do in this course. And also there's another aspect of that is most of the projects in this course don't have a requirement for bulletproofness. You know, that it just has to work for the correct inputs. What happens if you put malformed inputs into it? What happens if you attempt to do a buffer overrun error? What happens if you shake it and then, you know? So there's testing and there's also robustness that are just hard to get enough time to do. Maybe it's a better idea to do a few projects, a few less projects, and more robustness requirements. Go ahead.
I would argue that in computer science classes, you often learn about testing strategies and how to control the device. So I would say maybe not in the hardware design class, but as a computer science major, I've definitely had those courses.
So that's interesting. So
I can say the same for systems engineering. There is a lot of reliability and a lot of that being stressed on, but it's all on paper, never really on practice.
right.
But in 1985, that didn't exist. It was a new industry.
That's right. That didn't exist. All right. You're quite right. That didn't exist then. This.
And the end of the article says we never really had anything before that that's so terrible to really pay attention to it, and that's why FDA never really had a bullet list of like bullet point list,
Right.
like this has to be done, this and this,
Right.
this, or this device will not go to production.
It's very true.
So like in the real world, like say I'm a lowly programmer and I'm working on the X65. Honestly I'm just a little terrified that the guy above me is incompetent, or maybe the guy above him is incompetent, and maybe he has responsibility for the whole thing. And maybe this is a social question, and this is not sort of like a more ethics question. I don't want to submit a little piece of code which I know works. I don't want, I feel by programming, I have some responsibility to ensure the safety to everybody who uses this, regardless of how big or small might not be using it.
That's right.
If you have a large complex system, you can't have everybody say, okay, we're going to go through the test this. We need one person to say, okay, I'm going to be
It's a very complicated social question, and in many cases there is no answer that would satisfy everybody. There's an interesting article which I didn't assign this year, but which is linked up, called "The Case of the Killer Robot," in which a robot user is killed by the robot going nuts. It's just an arm that moves around and places stuff. It's an industrial robot, but it comes around and kills, smacks a guy in the head. And it's presented as a sort of a science fiction story, really, in which it starts with the headlines of the person being killed and then works backward trying to assign blame. And it is extraordinarily complicated. Well, I didn't know this case could possibly exist, and so I didn't code for it, but was it in the specification? Well, I'm not sure. Yeah, it's very difficult. I mean, these are the interesting ethics questions. That's, nobody wants to lie, cheat, and steal. It's the cases where you can't figure out what's right that are tough.
I would argue that today it's actually impossible to assign blame for at least biomedical devices, because 2 years ago I worked for a biomedical devices company, and the level of quality assurance and testing there is such that 10 people have to work on the same problem to make sure that none of those outlier cases. So in the event that something does go wrong, there's a team of people who oversaw it and improved it, and so the blame kind of gets distributed amongst. And
in some cases, you have to say, what is best effort? I mean, how many people do you put on it for how long to test it? And that's not well defined. Anyway.
Yeah, I feel a little privileged, entirely medical, trying to find out who
So in some abstract sense, I sort of agree that assigning blame is the wrong way to do it. What you should try and do is fix it. But that's not our social system, right? Somebody gets blamed for everything. and somebody pays. So so that says that after you get your degree here, go to law school.
I was going to say that some of this can be addressed by doing external reviews, because a lot of times stuff people who are actually working on the project can't see the whole big picture, like somebody sitting in a review board over the course of a couple of days. And that it seemed like once the FDA got involved, things got sorted out a little better because they were able to kind of take the 30,000 view of the issue.
Well, I think an external review, a non-technical review, people that aren't involved with the design should be going through the whole process and to find out how it should work or not work, and that is important.
Sometimes it's kind of because of the decisions that the management actually takes, whether when they should be actually taken by the technical team. So I remember one case, the Challenger disaster. So I think that was because of the O-ring failure in the space shuttle. So the engineers actually advised the NASA team to actually cancel the launch, but they actually, I don't know, very proud to cancel the launch or something like that, and they went ahead with it. So in the first meeting, they said that all the entire engineering team said that like cancel the launch. Then because of I don't know whether peer pressure or whatever.
Political pressure, whatever.
Yeah, so
6 canceled launches.
Yeah, they had already delayed the launch over time.
And it was such a big event because of the teacher from New Hampshire that she was
Right.
going to go to space. And
Right,
she
right.
took kids from there, and it had to happen.
So the management overrode the engineers. Yeah.
I think that's sort of at the crux of engineering in our society today is the interests of the administrators, the people who have the money, who can facilitate engineering. They're concerned about the return, whereas the engineers, they know what's actually going on within the system. None of the outside context matters. They just want it to work. And if the engineer says, the system isn't going to work, there's something we haven't figured out yet, even though we said that it would be done by now, there's a tremendous amount of pressure on the people with power to say, never mind, just continue with it. And that's what happened with their
Right.
was they don't want to tarnish their image, they don't want to, let people know that their machines were capable of going so.
They don't want to lose money. They don't want to
Right.
tarnish their image.
Try
all
to
of the
get
above.
somebody to go into one of your machines after you told them that it gave the last person 15,000 rads of radiation accidentally. Nobody's going to trust your work again. And I think that's particularly true in the medical industry.
Well, that's true. On the other hand, you have to ship stuff sooner or later. Right? You have to say, all right, it's good enough. And that's a judgment call. It's a judgment call.
It happens a lot though, where you engineer and it's not perfect, and you just have to say,
It's good enough.
It's still a product, and it's within tolerances, and there is a chance something will go wrong, but we think at least decrease the chance with significant.
Right. Right. It's a judgment call. Judgment call you all have to make. Good. Nice. Let's talk about Ariane 5 a little bit, and we'll talk about the plagiarism stuff on Monday. But